This slidecast covers an implementation of a double-linked list class. So we will implement a simplified version of the list class, KW list. This is the author's, the textbook's implementation of list. And that list class is for demonstration purposes only. In your programs, you should use the list class provided by the standard library. Now in our double linked list class, we're going to have a head and tail that are pointers to the first and last item in a list, and we keep track of the number of items in the list. Here's our definition of a list class, and we put it in a different namespace to distinguish it and keep it distinct from the standard library's list class. It's a template class. We include this dnode.h, which has this, the structure of the nodes. They're part of the private data defined in this class. And our public data includes list iterator, and we make a friend class of iterator and a list const iterator that's also a friend class. And then here we have our head and tail and number of items, the private data fields described in the last slide. So the dnode is private, the iterator is public. They're friends because both need access and modify the private members of the list class. Here's the default constructor for a list. We head and tail are null when the list is empty and there's nothing in the list. The copy constructor takes a list, a reference, a const reference to a list. We set the head and tail to be null and the number of items to be 0, and then we create an iterator pointing to the first item in this other list, and until we cycle through the entire list, and we push back every value that's in the list, we push it onto the current list. So when we're done here, we'll have a complete copy of this list denoted by other as a parameter. Here's the destructor to destroy a list. We say, well, the head is not null, then we set current equals head equals head arrow next, and we delete current. So we basically delete the first element of the list, and we continue cycling until the list is empty. Then we set tail equal to null, and the number of items is 0. Now the assignment operator, we're overloading that to assign the contents of one list to another. It takes a const reference parameter. First we make a copy of the other list. This uses the copy constructor into a local variable called temp_copy. Then we swap the contents of self with this copy. So swap temp copy, and then we return, and upon return the copy will be destroyed. So this temp copy will be a local variable that goes out of scope, and we return the current list. Now the push front function, here we have a list. The pointer to the head is Tom, the tail of the list is Sam, and push front takes a reference to an item, a const reference. This is the function. So we say head equals, it'll point to a new node. So here we'll create a new node. Its item gets assigned to data. In this case it's Ann. The previous is set equal to null. And the current head is placed in next. So the current head points to Tom, so now this new node Ann will point to head, and our head value here in list gets updated to point to this new node. And we say if head arrow next is not equal to null, so this value is not equal to null, then head next previous is set equal to head. So that updates Tom to point back to Ann. And finally, if tail equals null, that'll be true if we had an empty list when we push something to the front. Then we'd say tail equals head. But in this case, nothing changes. And then we increment the number of items, which now goes to 4. So here's the pushback function. Here's a list of Tom, Ann, and Sam. Push back is to put something at the end of the list. So we say if the tail is not null, okay, so the tail, that means the list isn't empty, then we say tail arrow next. So tail arrow next is this field here, which is currently null, and we set that to point to the new node. It includes an item and the tail and null as parameters. So here's a new node, Zoe. And next is going to be set to null, and previous is going to point to what tail used to point to. And then tail is going to be set equal to tail arrow next. So we'll advance tail to go from Sam to Zoe. We increment the number of items to 4, and we're done. Else, yeah, if the tail is not null, the list was empty, then we'll just call push front. The insert function, it takes an iterator as a parameter and an item, and the idea is we're going to insert that item at this position. So we check for special cases. If the position is currently the head, then we push it to the front, and we return begin, which is an iterator to the front of the list. Else, if the position.current is null, then we're past the last node, then we say push back, and then we return an iterator that points to this, and tail is its parent. So this is the sort of a constructor for the iterator class. So here's the insert function. We've got this list with 3 items. We have an iterator whose current position points to Ann. So the insert function, let's see, we create a new node. This is going to create a new node. The item in this case was Sharon. So here's a POS, and its current points to Ann, and then the previous there is, here's the previous value in Ann. It points back to Tom. We're going to take that pointer, and that gets assigned to the previous. So now Sharon refers back to Tom as the previous one. And the next is going to be a position current, which means Sharon now references Ann. So when we have insert and we point to a position, we insert it just before this node that's currently pointed to by the iterator. Then the position dot current arrow previous arrow next. So here's current points here. Arrow previous is this previous value here. Arrow next is Tom. Currently points to Ann, and we want Tom to now point to the new node. And then we have to update this previous, who used to point to Tom, and point that to the new node. And then we increment the number of items to go to 4, and we return an iterator that points to this new node. So the pop front function, if the head equals null, then we throw this invalid argument. We tried to pop the front off an empty list. Otherwise, we create a pointer to the first item in the list. That's called removed node. We modify head to point to the second item in the list, and then we can delete this removed node. And then if the head's not equal to null, which means the list is not empty, then head arrow previous is set equal to null, the first item in the list, and there's nothing previous to that. Otherwise, the tail is set equal to null, and we decrement the number of items. The popback function removes the last element of the list. So if tail is null, then that's an invalid argument. Otherwise, we set the removed node equal to tail. We modify tail to point to tail arrow previous. Now we can delete that removed node. And if the tail's not null, okay, that means the list isn't empty, then tail arrow next is set equal to null. It's the last item in the list. There's nothing to point to now. Otherwise, head is set equal to null. And we decrement the number of items. The erase function takes an iterator as a parameter. If it's empty, we can't erase something from an empty list. If this iterator is pointing past the end of the list, then that's invalid. Now we can say return value is an iterator, and we'll increment that iterator so it now points one past what we wanted to erase. And we say if position.current is the head, then we pop the front and return this iterator that points to the next item in the list. Otherwise, if the position current is equal to the tail, we'll pop the back and return the return value. Otherwise, we set up the remove node to where the iterator currently points to, and the remove node arrow next, we assign that to the remove node arrow previous arrow next. So this means we take the node that comes before the node we remove and point it at the node following the node we remove. And similarly here, if the remove node points back to an item, then we assign that to the next item in the list should point back to that as well to eliminate the current node. We delete this remove node and we return return value, which should be the new iterator. Yes, which was the original iterator advanced once. Now to implement an iterator, we have current, which is a pointer to the current item, and parent, which is a pointer to the list of which the iterator is a member of. Now we can change Harry to Henry by this statement. If this iterator currently points, if the current points over here to Harry, then we can use the dereferencing operator to say star iter equals Henry, and that'll update this data field here. This expression star minus minus iterator is equivalent to dereferencing comes after we do the decrement. This would move the iterator backward and then return a reference to its new position. Now the nested class iterator with some functions explored later. So here's a class iterator. It's a friend class of list. Here's its private data fields that includes a current node. Here's some constructors and some public functions. So here we have two functions to do operator overloading for the star and the arrow operators. And we've got other increment and decrement functions that we're overloading. They can return references or iterators directly. Now the list iterator constructor takes a parameter, a pointer to the as its parameter, a pointer to the D node at which the iterator is to begin, and this constructor is defined in the private part so that clients can't create arbitrary iterators. So the list class creates and returns this iterator object as needed, and we declared kw::list as a friend of this iterator class. So here's a constructor, an iterator that takes my parent is a pointer to a list, and position is a pointer to a node, and it just assigns those inputs to parent and current. And the dereferencing operator verifies that the current pointer is valid, and then it returns a reference to the data field in the D node that it points to. And since iterators can be used like pointers, the member access operator is also defined. So if current equals null, then we try to attempt to dereference end. Otherwise, we return the pointer to a current item. That's found in the data field member, or the data field data. Here's the prefix, increment, and decrement operators. And here's the postfix, increment, and decrement operators. Now the const iterator is identical to iterator except that the dereferencing operator returns a const reference and the member access operator returns a const pointer. The const in the operator heading means that the referenced item can't be changed, and the compiler ensures that any attempt to do so throws an error. And the complete code for the class const iterator is available on the text website, and the member functions and data members are identical to those for class iterator except for the two functions shown on the following slides. So here's the dereferencing operator, and it returns a const reference to an item type. So we say if current is equal to null, then we try to dereference. Again, it was pointing past the end of the list. Otherwise, we return data. Here is the member access operator, and we just return a const reference to the current data item pointed to by the iterator. So you need to use const iterator when a list is passed as a const. Now the following function prints the contents of a list of ints. So print list, it takes a const reference to a list. We create an iterator, and it's a const iterator. And then while that iterator is not past the end of the list, then we output the data item from the list. We advance the iterator, and we'll print these arrows in between all the values until we get to the last value. And that's the end of this slidecast.